All right, so I want to look at that example that we finished the last video with, and I read it again and realized I forgot to answer the second part to it. So we found the product AB, A times B. But notice it says explain why BA is not defined. Well, if I was going to find BA, look at the dimensions of the matrix that I would be the matrices I'd be multiplying together. I'd have a matrix B times matrix A. Matrix B has dimensions 2 by 2. Matrix A dimensions 4 by 2. Suddenly these inner dimensions don't match anymore. That would mean that I'm taking row vectors with 2 entries and trying to dot them with column vectors having 4 entries. You can't match the entries in a one-to-one correspondence that way. So this would not be defined. That's really important because multiplication with real numbers has the commutative property. In other words, if A and B, or let's say X and Y, if those are real numbers, then X times Y is the same thing as Y times X. You can reverse the order of multiplication and you get the same thing. That's not true of matrices. In this case, I was able to multiply A times B and get this 4 by 2 matrix. But if I tried to reverse the order of multiplication, B times A isn't even defined, so they couldn't be equal. Interestingly enough, though, even if it were defined, even if the dimensions did match up correctly, so I could multiply in either direction, most of the time I still won't get the same answer. So matrix multiplication is, in general, simply not commutative. Now, there are special cases where the product of 2 matrices does turn out to commute. Special matrices A and B, where if I multiply A times B or B times A, I end up getting the same thing. But that's not true in the general case. That's a really, really important property that matrices just don't have, and we have to remember that. Okay? All right, let's move on down here. So now, when we talked about partitioned matrices, we said that if you have a matrix A and you notate its rows R1 through Rm, then you can write the matrix A this way. Notice this is going to be an M by N matrix because there's M rows. This is not a column vector. Each of these represents an entire row of entries. All right. Now, the ith column of AB. So coming up here, this is the product AB. If I look at the columns of this matrix, they consist, all of the entries come from dot products of a row from A with a column from B. But notice, for example, if I look at the second column here, the column that's being dotted to each of these rows is the same in each entry of that column. It's C2 for all of them. Same thing here, C1 for all of those, CP for all of those. So and you kind of saw that happening in this example. I selected a column of B and just dropped it on each row to finish off this column here. So that provides a useful connection between the more general case of matrix multiplication to the matrix vector product, and that's kind of what we're getting at here. So again, the ith column of AB is going to look like this. Notice CI is the column that I'm using in each dot product, R1.ci, R2.ci, and so on. But this is the same thing as the matrix consisting of the rows R1 through Rm times the vector C1, Ci, the column vector, the way that we defined matrix vector products previously. That's exactly the same thing. This is equal to this. However, this partitioned matrix is equal to A, right? So that means each column of the matrix AB is the result of a matrix vector product of this type, which means AB can be written as a partitioned matrix, A times C1, A times C2, A times CP. Each of these represents a column vector, right? So these are not individual entries, these are all columns. But this gives us a useful notation for doing matrix multiplication that's going to help in some applications that come up later. Okay? And you can kind of think of this notationally anyways as very similar to the distributive property. So AB is equal to A times, now remember, the C1, C2, and CP and all that stuff, those are the columns of B, which means I can write B as a partitioned matrix this way, right? But then if you think of this almost like the distributive property, if I distribute A into each one of those columns, I get this thing up here, AC1, AC2, ACP. A will only distribute from the left in this way. It's important to know that going the reverse direction, we would have to handle that differently. But this, again, is a very useful way of thinking about matrix multiplication. Okay, let's see. All right, and continue moving on here. So now let's suppose we have n matrices, A1 through AN, and let's also suppose that they have the same size. All n of these are of the same size. And then for each one of those, we're going to select a scalar, just some scalar, C1 through Cn, and I'm going to form this expression, C1 times A1. Notice this is scalar multiplication. It's not matrix multiplication. A scalar times a matrix here, plus C2 times A2, plus blah, 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 until I get here, plus Cn times An. We call this expression a linear combination of the matrices A1 through AN. And you heard me use that terminology previously, and I said don't worry too much about the term linear combination here. It's going to be really important for this class, but I just kind of threw it out there. And now it's becoming more important. So a linear combination is a sum of scalar multiples of, in this case, matrices. We're going to bring this term up again in different contexts throughout the course, and in general, these things don't have to be matrices, but for right now, that's what they are. Okay? Now, we're talking about linear combinations here because it gives us a useful way of thinking about a matrix vector product, something that we're going to actually use to make some useful connections later. So if I have a matrix A, here's my general m by n matrix A, and if I have some column vector x, where x1 through xn are its entries, we've defined the matrix vector product this way. I take the dot product of this column with each of these rows, which gives me these. However, this is equal to this linear combination. And to see why, notice that I've taken this thing is in, there's m rows here and only one column because all of these are added up to a single number. So this is an m by 1 matrix. But each of these are also m by 1 matrices, and multiplying them by a scalar won't change their dimensions. They're still going to be m by 1 matrices, and adding them all together should produce another m by 1 matrix, specifically this one. So what this is saying, if you do the scalar multiplication first, x1 times a11, then this first entry is going to look like a11 x1, which is that. If I multiply x2 into this matrix, the first entry up here is going to look like a12 x2, or this. And you can see that happening for each of these matrices, and then doing the matrix addition has me adding all of those corresponding entries. That produces this. Okay? So what this is just an alternative representation of the matrix vector product in the form of a linear combination of m by 1 column vectors. Let me demonstrate this with an example. So here's my matrix A. It's a 3 by 3 matrix, and I want to multiply it by the 3 by 1 column vector x. But it doesn't actually say just perform the multiplication. It says represent AX as a linear combination of the columns of A. And that's what these are. Notice A11 through AM1. That's the first column of A. A12 through AM2, second column of A. So that's specifically what these are. These are the columns of A. So that makes this very easy. X1 in this case would be the first entry in my vector X. That's 4. And that's multiplied to the column 1, 4, 5, first column of A. Then my second entry in X is a 9, so plus 9 times the second column of A. 9, 0, negative 10. Plus my third entry in X, negative 5. Actually, instead of writing plus negative 5, let me just say minus 5, same thing, times the third column of A, negative 2, 5, 7. Okay, I'm not even going to do the scalar multiplication and the addition because It's not asking me for that. It just wants a representation as a linear combination. Okay, this may seem bizarre and unnecessary at this point, but it's actually an extremely, extremely important way of representing this product, and we won't really get to see why it's important until later, so you kind of have to just trust me on that. All right, another way of representing a product of two matrices. If A is an M by R matrix, and if it has these columns, C1 through CR, and if B is an R by N matrix and has rows C1 or R1 through RR. I know that's a little bit weird. I'm using R in two different ways here, but the bold R is a row. The subscript R is the rth row. So then the product can be expressed this way. Now this is a little different because in the case of how we define matrix multiplication, I was focusing on the rows of A and the columns of B, and I'm switching the focus now. Now I'm looking at columns of A and rows of B. And this is showing that AB, the product AB, can be represented this way: C1 times R1 plus C2 times R2 plus so on and so forth. So first column of A times the first row of B, and so on and so forth down the line. And performing, or by representing a matrix product this way, we call that column row expansion. Okay, I'm not going to prove this here. I'm not going to show why this works. In fact, we're not really going to do much with this in this course. Representing a matrix product in this way has some applications that you would probably encounter more in like a second course in linear algebra. But there are, I think there's a couple of homework problems where I want you to represent something using a column row expansion. So you need to at least be kind of familiar with the concept. Let's do an example to illustrate it. So it says, find the column row expansion of this product. It is not asking me to multiply these matrices and get the resulting matrix. It wants a representation of this product in the form of a column row expansion. So again, what I'm doing is I'm taking the first column of A, which is this guy right here, and multiplying it to the first row of my second matrix. I can think of that as matrix B. First column, 1, 0, 5, times this first row, 1, 5, plus second column of my first matrix, 8, negative 6, 1, times second row of that matrix, column B, or of that matrix B, if we want to call that B, plus third column of my first matrix, 3, 3, 2, times third row of my second matrix. Now looking at this for a second, you might think, it doesn't look like that should even be defined. I have 3 entries here and 2 entries here. But that's where it matters that we reversed the focus on columns in this first matrix and rows in this matrix. The dot products here look like regular real number multiplication. Remember, this is a 3 by 1 matrix, and this is a 1 by 2 matrix. You see how the inner dimensions match? So that's what's telling us that this is possible. But what does multiplication look like? Well, if I really did want to multiply this times this, I would take the first column here, multiply it to the first row here. But each of those has only one entry. So the 1, 1 entry of the resulting 3 by 2 matrix here would just be 1 times 1, or 1. Now let's look at this. Again, this would be a 3 by 2 matrix. That's what the result of that product would be, as would the rest of these. The end result is a 3 by 2, and here this would be a 3 by 2. Look at this product up here. It's a 3 by 3 matrix being multiplied to a 3 by 2 matrix. The inner dimensions match, and the outer dimensions determine that the result should be a 3 by 2 matrix. That's important because if I did all 3 of these products, then I have a sum of 3 3 by 2 matrices, which should be another 3 by 2 matrix, indicating that the dimensions of this result will match the dimensions of this result. What we haven't proven yet and we're not going to, like I said, is that the multiplication, regular matrix multiplication of these two matrices will actually come out to the same thing as if I simplified all of this, okay? If you go through the steps of multiplying these and adding the results, it may occur to you why the column row expansion actually works, but I'm going to let you kind of discover that on your own if you wish. All right. A little bit more to talk about in this section. So some different operations that we can perform on a matrix. This one's really important. Everything that I'm covering is really important for the most part, so I probably don't need to say that. But let's suppose A is an m by n matrix. Then we define the transpose of A, and we use this notation for it. A, it looks like a little exponent, but it's not an exponent. It just, that's the notation. T is the n by m matrix. Notice the number of rows and number of columns has switched. Okay, it's the n by m matrix such that for every I in J, the ijth entry of A transpose is equal to the jith entry of A. What? Well, if you're confused by that, let's try it with an example. So first of all, this is a 4 by 2 matrix. A right here, that's a 4 by 2 matrix. So according to the definition of a transpose, I should expect my result to be a 2 by 4 matrix. 2 rows, 4 columns. The ij becoming ji here means that the row and column position of a number switch to a column and row position. So the 1, 1 entry, the entry in the first row, first column is not going to change because if I switch 1 with 1, they're still both 1. This is the entry in the first row, second column. The transpose should put it in the second row, first column, which would be here, second row, first column, 5. Notice what actually happened though. My first row of A became the first column of a transpose. And in fact, the same thing's going to happen. So as I read a row from left to right, that's going to become the column as I read it from top to bottom. So here, my second row, as I read it from left to right, is 0, 9. That'll become the second column of my transpose. Third row, 2, 2, becomes the third column. And my fourth row, negative 4, 1, becomes the fourth column. Okay? Now, there's different ways of thinking about this. One way of thinking about it is, and it's more useful thinking of it in terms of square matrices, but if you look at what would normally be thought of as like the main diagonal, the 1, 1 entry and the 2, 2 entry in this case, the transpose basically reflects this matrix across that main diagonal, flips it over that main diagonal. I can't animate that for you, but I've seen animations of that kind of help illustrate that idea. But I found in practice it's actually easier to think of it as swapping rows for columns and vice versa. Okay, so that's the transpose. You can do the transpose of any matrix, and it's just going to swap the columns with rows. And then here's an operation that's only defined for square matrices. And we don't use this one a ton in this class, but it will pop up in a couple of places. So if A is a square matrix specifically, then we define the trace of that square matrix to be the sum of the entries on its main diagonal. And again, this is one of those things when you first start learning about matrices and you're taught what the trace is, you're thinking, how could that possibly have any useful application? What's the point of only adding up the numbers on the main diagonal? Why am I supposed to ignore all of the other entries in that matrix? And it's one of those things where I have to just say, trust me, you'll see some usefulness out of this later on. Right now, it's just a matter of definition. So if we want to find the trace of this matrix, it's 3 by 3, so it's a square matrix. That means we're allowed to take its trace. I want to find its main diagonal and add those numbers. 5 plus 1 plus 4 is equal to 10. Notice the trace gives me a scalar. It doesn't give me another matrix. Okay, so I could call it a scalar valued function, but you don't need to know that terminology. Okay, so that's the trace. Now, we want to be able to do multiple operations on a matrix at a time. And we're going to do more of this later, but what I'm going to do here is define this matrix A and set it equal to a 2 by 2 matrix, 1, 3, negative 2, 6. and I want to find the trace of A transpose times A. Okay, and there's a couple of kind of interesting things that we can notice from this one example. So let's start by multiplying A transpose times A. What is that? A transpose times A. Well, A transpose is what I get from swapping columns and rows of this matrix. Although, because it's a square matrix, I can also think of A transpose as the matrix A being reflected across its main diagonal. Its main diagonal doesn't change, but the other entries will trade places, 3, -2. And then I'm going to multiply that to the original matrix A, 1, 3, -2, 6. Okay? Now I need to multiply these, so I'm going to do 1 times 1, that's 1, -2 times -2, that's going to be 4, and so I get 5. Okay? And then I'm going to multiply this first column to the second row to get my 2, 1 entry down here. 1 times 3 is 3. -2 times 6, that would be -12. What did I say? 3 minus 12, that would be -9. And then if I do my second column times my first row, I'm going to get 3 times 1. It's 3. 6 times -2. That's -12. Looks like I get the exact same thing, -9. And then if I get this last one, 3 times 3 is 9. 6 times 6 is 36. That adds up to 45. There. Okay. Make sure I got that right. Yeah. All right. So now what I need is the trace of that. Well, the trace is the sum of the entries on the main diagonal. 5 plus 45. Okay. That's equal to 50. So there's my trace. Now, there's more to this problem. It says verify that this is equal to the sum of the squares of the entries of A. Well, that means if I look at A, all of its entries has 4 entries, and I sum the squares of those entries, 1 squared plus 3 squared plus -2 squared plus 6 squared, that would be equal to 1 plus 9 plus 4 plus 36. This adds up to 40, that adds up to 10, 50, same thing. Interesting. Is that a coincidence that the trace of A transpose times A gave me the same number as the sum of the squares of the entries of the original matrix A? Well, no. In fact, that's always going to happen. It says, does this generalize? I'm not going to tell you why, but that's actually an important application of this specific pair of operations here, the trace of A transpose times A. And I'm going to let you kind of think about that. Why would that happen? One other thing I want to point out, this is something that we're going to prove at the end of chapter 1. Notice that the product of A transpose times A has kind of an interesting form. You see how I have -9 here and -9 here? Not quite as apparent with a 2 by 2 case, but if A was a 3 by 3 matrix and I did A transpose times 3, you would see a similar relationship. This matrix has symmetry about its main diagonal. Another way of thinking about that is if I took this matrix, the result of that product, and took its transpose, I'd get the exact same matrix again, because the only thing that would happen is these -9s would trade places, and nothing is actually changing. These matrices are called symmetric matrices. We introduced that in section 1.7, so you don't need to memorize that yet. It turns out that for any matrix A, if I do A transpose times A, I always end up with a symmetric matrix. And the same thing happens if I do it in the reverse order, A times A transpose. That is important as well, but it's of more importance in a second course in linear algebra. Not quite as important here, but we work with A transpose, matrices of the form A transpose times A a lot in certain applications that would come in a later course, things like dealing with singular value decompositions, which is not a topic for this course. Look it up if you're interested. But this last example is going to finish up section 1.3 for us.